We're continuing in our discussion of hardware. Every computer has a clock generator to generate clock signals used throughout the system. Timing in a computer system is critical, particularly to synchronize the activities within the various chips. To do this, a crystal is used, and this is a picture of a crystal right here. The most common crystal is a 14.318 megahertz crystal. And the reason that this particular frequency is chosen is because within the world of crystals, this is an extremely stable frequency. And it serves as the foundation frequency for generating all of the other timing circuits in a PC. So this frequency would be multiplied or divided as necessary, and we would get frequencies like 33 megahertz for the PCI, 8 for the ISA, and 48 megahertz for USB. And this is actually a part of a data sheet for a 133 megahertz clock synthesizer driver for PC motherboards. And I just refer to this simply because in our studies we've been looking at various chips and integrated circuits, and this is an integrated circuit that starts out with this 14.318 megahertz crystal, and it generates all of the frequencies that you see here. And for example, here we have 100 and 133 megahertz, which are common starting frequencies for microprocessors. Usually they're multiplied by one of these to get the necessary frequencies. Here is 33 megahertz. That would be, for example, PCI. Then we have 50 and 66 megahertz. There's 16.67. That's actually the ISA frequency. 66. This very well could be AGP, and then that's the processor. And then 48 megahertz. That would be the USB. But at any rate, here we have a chip that would be found on system boards, and usually you don't know what this chip is. It's just a chip that's sitting there, and it's not identified. But do keep in mind that these chips do exist, and they're necessary to establish all of the bus frequencies for your board. And just note here also, I just observed this has 3-state outputs, which we had talked about previously. Okay, next item, microprocessors. The microprocessor is a standalone functional block and is the brains of the computer system. And so here we have a nice little image of a microprocessor, and actually the microprocessor, the actual chip is right here, and you can see these little hairline wires that are connecting to it, and then those wires connect to these pins, which would actually plug into the circuit board. Microprocessors direct the activities within computer systems, even when discrete components are used for functions such as video. So many of your other cards will actually have discrete components. This is going to be completely an integrated circuit. And you'll notice here is the microprocessor in this block diagram. Okay, processor cooling. Many microprocessors draw a lot of current and get very hot because of the high switching speeds inside the IC. A fan is necessary to keep the device cool. And so here we see this is the heat sink, and then this is the fan. Actually, the microprocessor is this little piece down here. It's right down in this area. The heat sink is used. It's attached to the microprocessor, usually with a spring, and usually these hold the heat sink in very tightly against the processor. And usually there's some thermal compound that is put on the processor between the processor and the heat sink, and this will encourage the transfer of heat between the processor and the heat sink. And so in theory the heat starts on the processor, it goes up into the heat sink, and then the fan is here to blow the heat off, and here's the connection for the fan. Cooling in a microprocessor is very critical. Most processors, if they do not have a fan, they will fail. Now, it is common that they have a when they get to a certain temperature, the processor will just shut down and won't necessarily destroy it, but it will turn off. And so a common fault that occurs is that if a computer is turned on and after maybe 2 or 3 minutes it just shuts off for no apparent reason, oftentimes the problem is found right here, that the fan is not functioning. And so as the temperature comes up, the thermal temperature reaches a certain point and the machine just powers off. Now that's if you're lucky. If it doesn't power off properly, then you probably have a toasted processor. Okay, system controller. The system controller is a complex IC, we're talking about this one right here, that takes orders from the microprocessor and carries out those orders with little or no further supervision from the microprocessor. So you see the microprocessor interfaces directly with this thing we call the system controller, and it also interfaces directly with memory. The strategy is using distributed control. The strategy in using distributed control is to allow multiple activities to occur simultaneously in different parts of the system. And the system controller is going to be carrying out many of these functions. Though not mentioned in your text, this device is called the chipset. And so this, we'd have the chipset right here, and that your text doesn't use that term. Actually, the chipset is divided into two areas. There is the what they call the north bridge and the south bridge. And the north bridge handles the very fast interfaces, that would be like between internal memory and cache, and the south bridge will handle the slower devices like PCI and ISA and etc. Okay, this concludes this particular section. We're going to, in the next section, we're going to be looking at memory. We're going to be picking up with the system controller and looking at the interface between the processor and memory.